Alrighty, Bulldogs, we are finishing up our chapter 3.3 unit, and that means we have one last thing to cover. So we've learned the power rule, we've learned the product and the quotient rule, but now let's actually apply those in different scenarios. So I'm on page 9 of your notes packet. And question number 1 says, find the equation of the tangent line to f of x equals 3x squared minus 6 at 1, negative 3. So in our last unit, in order to find an equation of a tangent line, we had to evaluate the limit as h approaches 0 of f of a plus h minus f of a all over h. And then substitute in an x value of 1 for a. Well, now that we know the power rule, we don't need to do that anymore. So the first thing I'm going to do is find my derivative of f prime of x, which would be 6x. And this now represents a formula for the slope of the tangent line anywhere along the curve. I specifically want to find the slope at 1, so I am going to substitute a 1 into this function, which leaves me with f prime of 1 equals 6, or the slope of the tangent line when x equals 1 is 6. So I now know the slope. I know my point is 1, negative 3. I'm going to use point slope form. So y minus negative 3 equals my slope of 6 times the quantity x minus 1. Okay. If you take a look at part B, a normal line is a line that is perpendicular to a tangent line. For example, if we were sketching this graph, this is a parabola that's been shifted down 6 units. And we just found the slope of the tangent line at the point 1, negative 3. So this is what we just found, the slope and the equation of that tangent line. Well, if I wanted the equation of the normal line, it's the line that is perpendicular to that. So if you'll recall from geometry, parallel lines have slopes that are parallel lines have slopes that are identical. Perpendicular lines have slopes that are opposite reciprocals or negative reciprocals. So I already know, since I'm looking at the same exact point, I already know the slope is 6. So the perpendicular slope would be negative 1 over 6. And my point is still the same, 1, negative 3. So my equation of my line would be y minus negative 3 equals negative 1/6 times x minus 1. Okay. This is not example number 1, since that is example number 1, but that's okay. So we've got a bunch of data provided to us about f, g, f prime, and g prime. So if we look at example A, this is asking us to find f plus g prime of 5. So another interpretation of writing this would be when you have a sum, you can take the sum of the derivatives separately and add them. So this is equivalent to f prime of 5 plus g prime of 5. And both of those pieces of information are given to us up here. F prime of 5 is 2, g prime of 5 is 3, 2 plus 3 is 5. Look at letter B. This is a difference problem, and it's the same scenario where the derivative of the difference is the same as the difference in the derivatives. So f prime of 5 minus g prime of 5 is an equivalent expression, and f prime of 5 is 2 minus g prime of 5 is 3, so we're left with negative 1. But once you get to something like letter C with a product, we know the derivative is of a function that is in the form of a product of two expressions requires that we use the product rule. So the first thing I'm going to do is I'm going to rewrite this using the product rule. So first function times the derivative of the second plus the second function times the derivative of the first. And that leaves me with f of 5 times g prime of 5 plus g of 5 times f prime of 5. And now I'm going to substitute each of those numbers in. So f of 5 is equivalent to 6. G prime of 5 is 3. G of 5 is negative 1. And f prime of 5 is 2. So we have 18 minus 2, which is 16. And then our last example is a quotient rule. So when I write this out using my quotient rule, it would be low, which is G, D high, which is F prime, minus high, which is F, G prime, all over low squared. If you wanted to rewrite that with the 5s, you certainly can. So we would have G of 5 times F prime of 5 minus F of 5 times G prime of 5 all over G of 5 quantity squared. And now I'm going to drop those values in from my list. So G of 5 is -1 times F prime of 5 is 2. F of 5 is 6. G prime of 5 is 3. All over G of 5, which is -1 squared. So we have -2 minus 18, which is -20 divided by 1. So that is -20. Okay. Some other variations that you might see are product rules and quotient rules where the data is not handed to you in a list form. It might be given to you in a chart, or you could be asked to extract the information from a graph as well. Okay, take a look at example number 2. We're being asked to find so f of x is defined as the cube root of x squared times h of x, and h of 27 is defined as 3, h prime of 27 is defined as -2, and they're asking us to find f prime of 27. So I'm finding the derivative of this, but this is a product of two expressions. So the first thing I am going to do, I'm going to rewrite this so that my cube root of x squared is written in a rational exponent form. So x to the 2/3 times h of x. And then in terms of using the product rule, this is my first expression. This is my second expression. So for my derivative, we're going to use first times the derivative of the second plus second times the derivative of the first. So first is x to the 2/3 power times the derivative of the second plus the second, which is h of x, times the derivative of the first, which is 2/3 x to the -1/3. And since I'm being asked to find f prime of 27, that means I'm going to replace x with 27. So I'm going to replace all of these x's with a 27. So we have 27 to 2/3 power times h prime of 27 plus 27, h of 27 times 2/3 times 27 to the -1/3 power. Okay, so 27 to the 2/3 power, that's the cube root of 27 is 3, 3 squared is 9. H prime of 27 is defined as -2. H of 27 is defined as 3. I'm going to bring down my 2/3. And then 27 to the -1/3. So that is 1 over the cube root of 27. So the cube root of 27 is 3, but this is pushing into the denominator, so that's like a 1/3. And I'm just going to bring this party up here. So on the front half, we've got a -18. And then my 3's here are going to cancel, so I have plus 2/3. So we could write this as -17 1/3. Go with the good old mixed number, which we never do in here. Okay, so this is just kind of a weird abstract problem where part of the expression is in function form and the other part is actually just the notation of a function. All right, now we get to some more challenging problems. So look at example number 3. Find the points on the curve where the tangent is horizontal. Well, if you think about a curve, when is the tangent horizontal? Well, the tangent is horizontal when our slope is 0. And we're now saying slope of the tangent line is the same thing as f prime of x, or in this case, y prime. So I am going to find my derivative function, and now we're being told that that slope is equal to 0 if there is in fact a tangent line that is horizontal. So I'm going to find my derivative and set that derivative equal to 0. So y prime is equal to 6x squared plus 6x minus 12. This is a formula for slope. They're telling me the slope is 0. So I've got a little quadratic to solve. You can factor out a 6 or you can divide through by 6. If I divide, I would have x squared plus x minus 2. And then we'll factor x plus 2 times x minus 1, which leaves us with x equals negative 2, x equals 1. And the question actually says find the points on the curve. So then you go that extra step and substitute negative 2 into your function. To find the y value, substitute 1 back into the function. I think you guys can take it from there. Okay, let's jump to the next page. So for example number 4, it says, ooh, that did not print very well. Show that the curve y equals 6x cubed plus 5x minus 3 has no tangent line with a slope of 4. Well, we know from the previous problem that the derivative is a formula for slope. And now they're telling me slope is 4. So I'm going to start by finding the derivative. That is so hard to read. That says 6x cubed plus 5x minus 3, I think. So that would be 18x squared plus 5 for my derivative. That is a formula for slope. They want me to show or prove that there is no tangent line with the slope of 4, so I'm actually going to set this equal to 4, and maybe that will help me understand why there isn't one. So I'm going to subtract 5 from both sides, divide through by 18. Oh, there we go. That's why. When you take the square root, we get an imaginary number, which means there are no real numbers where this graph has a tangent line with a slope of 4. Okay, take a look at example number 5. Draw a diagram to show that there are two tangent lines to the parabola y equals x squared that pass through the point 0, negative 4. Find the coordinates of the points where these tangent lines intersect the parabola. Okay, so I am going to sketch this because maybe this will help me kind of visualize what's happening. So we have a parabola, y equals x squared. The tangent lines pass through the point 0, negative 4. So if there is a tangent line passing through this point and it's tangent to this curve, we're looking at a line that looks something like this. And then on the other side, it looks something like this. Okay, so the first thing that I know is they're asking me to find the coordinates of the points where they intersect. So I'm actually being asked to find these points right here. So the first thing that I know is that these intersect each other. So the parabola, y equals x squared, intersects these lines. So I'm thinking I might start by generating an equation for this line. Now I do have a y-intercept, but if you didn't realize that, we could just drop in any old point. So I'm going to start with point slope form. So y minus negative 4 equals, and I don't know the slope yet, times x minus 0. So that would clean up to y plus 4 equals mx. Now we don't know the slope, but I know that to find the slope of this tangent line, I would be looking for the derivative of that function at a specific point. So to represent slope, I'm going to find the derivative of that curve, which is 2x. And 2x is an expression that represents the slope. So I'm going to substitute that 2x in over here in place of my slope. So now I have y plus 4 equals 2x squared. So this is an equation for the line, and that x value that I dropped in is sitting on that line. And then I also have an equation for the parabola, and I'm looking for where they intersect, so I can actually create a system of equations using y equals x squared and y plus 4 equals 2x squared. So I'm solving the system of equations between these two. Now you can use substitution, elimination, whatever you like. This is beautifully set up for substitution. So if y is equivalent to x squared, then I am going to replace y right here with x squared. And I'm going to come over here to do this. So we would have y plus 4 equals 2x squared. here's my other equation, y equals x squared. I'm going to drop this expression in here for y. So x squared plus 4 equals 2x squared. And I'm going to solve for x. And I can collect like terms on this side. So I've got 4 equals x squared. Take the square root of both sides, and I get plus or minus 2. That provides for me the 2 points where these lines meet this parabola. So the question said find the coordinates of the points where these tangent lines intersect the parabola. One of those points has an x-coordinate of 2. The other one has an x-coordinate of -2. So you can drop 2 back into either function. So 2 squared would give me 4, -2 squared would give me 4 also. So these are my 2 points. Okay. Take a look at my next question. So it says find equations of both lines through the point 2, -3 that are tangent to the parabola y equals x squared plus x. Okay, so I have some kind of parabola and the lines intersect with this point. This kind of sounds like the previous question. So I've got a parabola, I've got points. I don't know exactly what it looks like because I didn't really draw the real parabola. But what I'm going to try and do is use 2 different equations and look for where those 2 equations intersect each other. So I already have one of my equations here, just like we did up above. And then I'm going to try to generate an equation for the lines. So y minus -3 equals m, I don't know what m is yet, times x minus 2. So that's y plus 3 equals m times x minus 2. And I want to have some kind of expression for slope at these points. So I'm going to find my first derivative, which is 2x plus 1. And this is an expression for slope. So I'm going to substitute that expression in over here for slope. And now look what I have. I have an equation for the parabola. I have an equation for the lines. Both of those equations are written in terms of y and x. So 2 equations, 2 variables. We can solve this using another system of equations. So my first equation is this y equals x squared plus x. I'm just going to clean this one up a little bit. So we distribute 2x squared. We've got -4x plus x, which is -3x minus 2. And I'm even going to slide this 3 over. So 2x squared minus 3x minus 5. And now I've got y equals x squared plus x right here. I've got y equals 2x squared minus 3x minus 5. So I'm going to set these y expressions equal to each other just using substitution. So I would have x squared plus x equals 2x squared minus 3x minus 5. And this is a quadratic, so I'm going to get everything on one side. So I'm going to subtract x squared, so that leaves me with x squared. Subtract x, that's minus 4x minus 5. And that is factorable, which is beautiful. So x minus 5 times x plus 1 leaves me with x equals 5 and x equals -1. Now for this problem, they wanted you to find the equations of both lines through the point that are tangent to the parabola. So they want you to follow up and find the equation. So for the point, if I plug 5 in to the original equation, I would have 5 squared is 25 plus 5 is 30. Over here, I would have -1 plugged in, so that would give me 1 minus 1, which would give me 0. And then I also need to find the slope at those points. So I would substitute 5 into my slope formula. So 2 times 5 is 10, plus 1 is 11. And then for this one over here, plug -1 in. So -2 plus 1 is -1. So now I have the point and a slope. I can write my point slope form. Y minus 30 equals 11 times x minus 5. Over here, y minus 0 equals -1 times x plus 1. Okay, I'm going to hop over example number 7 for right now. Last one on this page. Find the equation of the tangent line to the curve y equals x squared plus 3x minus 4 that is parallel to the line 6x minus 3y equals 2. Well, we talked about it earlier. A normal line is perpendicular with opposite reciprocal slopes, parallel lines have the same slope. So first thing I'm going to do is grab this equation and find what its slope is. So I'm going to put this in y equals mx plus b form. So negative 3y equals negative 6x plus 2. Divide through by a negative 3. So we would have 2x minus 2/3. And I can now extract my slope from there. So my slope is 2. So I'm being asked to find the equation of the tangent line that is parallel. So I'm looking for the equation of the line that has the slope m equals 2. So I'm going to find my first derivative, which is 2x plus 3. And I am going to set my first derivative equal to this slope. And so that slope is 2. And solve for x. So negative 1 equals 2x, x equals negative 1/2. So I now know the x coordinate where the slope is 2. In order to finish out this equation, I do need a y coordinate, and then we can write the equation of the line. So I need to substitute negative 1/2 back into that function. So we would have negative 1/2 squared plus 3 times negative 1/2 minus 4. So that would be 1/4 minus 3/2 minus 4. I'm going to find a common denominator. 1/4 minus 6/4 minus 16/4. So that is negative 5 plus 16 is negative 21/4. So my y coordinate is negative 21/4. Now I can finish out my equation of my line. So y minus or plus 21/4 equals my slope of 2 times x minus or minus a negative or x plus 1/2. Okay. Okay, our very last question is example number 7, which is actually page 156, number 62 in the textbook. So I'm going to scoot this out, and I'm going to drop in my textbook here. So we are looking at example number 62. So the question says that we are going to let p of x equal f of x times g of x. And we're going to let q of x equal f of x divided by g of x, where f and g are the functions whose graphs are shown. So part A asks us to find p prime of 2. Now, in order to find p prime of 2, I first need to find an expression for p prime of x. And p of x is defined as a product. So in order to find an expression for the derivative, I need to use my product formula. My first expression is f of x, my second expression is g of x. So p prime of x would be first, which is f of x, times the derivative of the second, plus the second times the derivative of the first. So that would be f prime of x. And what I'm really being asked to do is find p prime of 2. So I am going to replace all of my x's with 2's. So f of 2 times g prime of 2 plus g of 2 times f prime of 2. And now I'm going to extract this information. Now you saw a problem earlier in this lesson where the data was just given to us in a list form. In this case, we have to grab our data from a picture. So the first thing I'm looking for is f of 2. That is the value of the y coordinate when x is 2 on the f function. So here's f of 2. That looks like a y coordinate of 3. Now they're asking us to find g prime of 2, which means on the g function at 2, which is right here, what is g prime, which is the derivative? So derivative on a graph is slope. So here's my g function at 2. What is the slope? We'll pick any 2 points. That's a line. So that would be a rise of 1, a run of 2. So that would be a 1/2. G of 2 means on the g function, I'm going to grab the y coordinate, which is 2, times f prime of 2. Oh, I'm so sorry, you can't see that. Back out a little bit here so you can see a little bit more. There we go. F prime of 2 means on the f function, when x is 2, what is the derivative? In other words, what is the slope of the curve? So let's find on f where 2 is, which is right here. The derivative, well, that tangent line looks like it's horizontal, so that derivative would be 0. So P of 2 is 3 over 2 plus 0, or 3 over 2. Okay, we've got one more question, and it is find Q prime of 7. So this is part B. And so let me fold this over here. So we're going to be finding Q prime of 7, which means I need an expression for Q prime. So let me go ahead and write this down first. So Q is defined as f of x divided by g of x, which means Q prime of x would be low d high minus high d low over low squared. So low would be g of x, d high minus high d low all over low squared. And I'm really looking for Q prime of 7, so I'm going to replace all of these with 7s. So g of 7 times f prime of 7 minus f of 7 times g prime of 7 all over g of 7 quantity squared. Okay, time to grab our values off of our picture. Let me zoom out a little bit more. There we go. So what we've got, g of 7. So 7, 1, 2, 3, 4, 5, 6, 7. All right, so it's right here. So g of 7, that's a y value, is 1. F prime of 7 is the derivative or the slope on f at 7. So I need the slope of this little line. So I need to grab 2 points. So there's a point here. Here's a point way over here. That's a rise of 1 and a run of 4. Minus f of 7. So that would be my y coordinate here. So that's 5. Times g prime of 7. So here's g of 7. G prime of 7 would be the slope. So we're going to grab 2 points. So I'm going to grab this point and this point. So rise would be -2. Run would be 3. So -2/3. And that is all over g of 7 squared. And g of 7 is 1 squared. Okay, now we're just going to clean this up a little bit. So we've got 1/4. Negative times a negative is a positive, so we have 10/3 on the top, all over 1. So we just need to find a common denominator here. So let's use 12. So this would be 3/12. Over here, that would be 40/12. Fun numbers. So we would have 43/12. Okay, so you have now seen a wide variety of more challenging applications of the power rule, the product rule, and the quotient rule. I hope you found this helpful, and I thank you so much for listening. Sorry, this was a long video, so if you stuck it out to the end, give yourself a pat on the back. Thanks.